about enolate. As we said earlier, that enolate are anions formed from the deprotonation of our hydrogen in a carbonyl compound. That's the deprotonation of our alpha hydrogen in a what? In a carbonyl compound. So we can only say that is the first of all, in any compound, to form an enolate anion, you need to figure out where the what? The alpha hydrogen is. So we can see this is where our alpha hydrogen is. So we can easily deprotonate here. So now the next one is that. So what reagent are we going to use? We are making use of dilute NaOH, that is dilute sodium hydroxide. So then we can simply split our dilute sodium hydroxide. We are left with Na plus and what? OH what? Minus. So with this basis, this OH minus can easily attack our alpha hydrogen, and we are left with this. We are left with this. We are left with. So you can see there have been a loss of what? Of hydrogen at this place. That is, this is to show that a deprotonation has occurred. Compared to this, at this point we have 3 hydrogen, but at this point we have what? Just 2 hydrogen, and they are what? Our anions. That is, this is to show that an enolate has been successfully what? Formed. This is to show that an enolate has been what? Successfully what? Successfully formed. So there are ways we can this enolate can be rewritten. So we have different kinds of ways that the enolate can be rewritten. It can also be written in these forms. You can have this. It can also be written in this form. It can also be written in this form. We can have it like this: C and R. So now we have a CH2 minus at this point. So now this minus can move to this direction, and it is being erased, which leads to what? Which leads to a negative charge. So it leads to what? A negative charge, and there's a shift of electrons at this point also. We also have a shift of electrons, which results this double bond in the ketone, the double bond in the oxygen, to turn to a what? A single bond, and resulting the oxygen carrying a negative charge, which is as a result of what? Excess what? Electrons. So we can have our enolate in this form. We can either have it in what? In this form or what? Or this form. So in simple terms, we successfully generate our enolate anions by the deprotonation of what? Alpha hydrogen in a what? In a carbonyl compound. So now in any scenario, maybe in a retrosynthesis reaction, this is one of the most basic ways we can synthesize, that way we can form our what? Our enolate ion by simply deprotonating an alpha hydrogen in a what? In a carbonyl compound, and this makes it very active at this point. It can react at any point. So our enolate is very what? Is very active at this point, which it can react. But how we form some common examples of our carbanions. So the next one you have is our organometallic reagent. And when we talk about organometallic, the first instance there is, what are organometallics? What do we mean by the statement organo? When we say organometallic, so organometallic simply means carbon being bonded with a what? With a metal. We can say when a metal complex is being sandwiched in a what? In a carbon. So that is metal complexes being what? Sandwiched. So now when we talk about organometallic, it simply means a metal bonded with a what? With a carbon. So now there are substances that contains carbon atoms bonded what? To a what? To a metal. So these are our normal scenarios. We have it as Rn. So where the key part carries the what? Negative charge, and the metallic part carries the what? The positive part. So some common examples of our organometallic reagent are these. So now, and there are ways we name our organometallic reagent. So now we have metal. So now this is an organometallic compound where you have lithium bonded to what? To an alkyl part, to a carbon chain. So now, how do we name this compound now? We already know that lithium is the what? Is the metal being bonded. So now to name this compound, we name it based on the kinds of metal being bonded. We can say the name of this compound is said to be what? It's said to be organolithium. This is said to be what? Organolithium reagent. This is an organolithium reagent. We already know that the alkyl part will have the negative charge and the lithium will have the what? Positive part. So now let's see some other respective examples. And we also have this one as a where we have RMG what? X. So this is a popular, one of the most popular reagent known as what? Grignard reagent. One of the most popular reagent known as Grignard what? Reagent. And if you don't call it Grignard reagent, it can also be called as organomagnesium. It is also known as what? Organomagnesium. So don't forget, on the basis of naming organometallic compound, organometallic reagent, we talk about we name based on the metals being attached to the carbon atoms. So we start with organo, and what is the name of the what? Metal being attached. We can say this is said to be what? An organolithium. This is said to be what? An organo what? Magnesium or Grignard what? Reagent. So this is their key part. This is our magnesium part, and this is what? We can use any halogens. It can be egg, it can be bromine, it can be chlorine, and the next one we have here is this is the next one we have here. So can you give me a suggestion of this name? That is, what is? Can you give us a suggestion of this name? A suggestion of this name. So now, in simple terms, based on the metal we have here, we can say it to be. This is said to be what? Organocopper. It is what? Organocopper. If you don't call it organocopper, it can also be called organocuprate. Or you can either call it organocopper or what? Organocuprate. So you'll be able to broach the system of naming in organometallic chemistry. So these are one of the most basic system of naming in what? Organometallic chemistry. I'll say that carbanions are said to be nucleophilic. So now, these are the reactions involving carbanions as a nucleophilic. We have different varieties of what? Of reaction, that is, with which carbanion cannot undergo. The first one here is the alpha halogenations of what? Ketones. You should have the idea what we mean by what we meant by alpha halogenations of ketones. That is the additions of ketones, the addition of what? Halogens to the alpha carbon. That is the addition of what? Alpha of halogens to the what? Alpha carbon. So that's the first one of the what? Basic reaction in carbanions. The next one is what? The nucleophilic addition to what? Aldehydes and what? And ketones. These ones are into 4 varieties. We talk about, in the first variety, we talk about the aldol and the cross aldol condensation. And the next one is about the aldol related reactions. The third one is Grignard synthesis of alcohols. And the fourth one is the Wheating synthesis of alkenes. So all this will be considered in the reactions involving what? Carbanion as what? As a nucleophile. So it's one of the most basic and one of the most what? Interesting parts. So the third one reaction is the nucleophilic acid substitution. Is what? The nucleophilic acid substitution with esters and what? And acid chlorides. The nucleophilic acid substitutions with what? Esters and what? Acid chloride. And these are into 2 bases. You have the cleansings and the what? And cross cleansings. The first one is what? The under nucleophilic acid substitution of what? Esters with what? Acid chlorides. The first one here is what? The cleansing and the what? Cross cleansing. And we can also consider coupling of lithium dialkyl cuprate. Coupling of what? Lithium dialkyl cuprate with what? Acid chloride. The last one we can also consider, we will also consider the Michael addition. We will consider the Michael addition to alpha beta unsaturated carbonyl compound. That is the Michael addition to alpha beta unsaturated carbonyl compound. In also this scenario, we also consider the Robinson annulations. So the Robinson annulation we also will be put in what? In place. So this one of these are the first one. First reaction of carbanion will be put under consideration is what? The alpha halogenations of ketones. That is to halogenate the what? The alpha carbon. So we can see this is one of those general equations. We have our ketone group, and we know that this is the what? Our alpha carbon, and this is the what? Alpha what? Hydrogen. When we talk about alpha halogenations of ketone, that is, we want to replace the alpha what? Hydrogen. We want to replace the what? Alpha hydrogen with a what? An halogen, which is X2. So our halogen can be chlorine, can either be bromine, or can either be what? Iodine group. So we can have it in that there we can be chlorine, bromine, or what? Our iodine group. That is replacing these alpha halogens with a what? With a bromine. So these are our general equations. Then we go to the mechanism. So we can see the general equation here. The alpha halogen has been replaced with a what? With a the alpha hydrogen has been replaced with a what? With an what? An halogens, and we have our residual plus what? HX. So that is, don't forget, we have excess. For example, we are making use of bromine. We have Br what? We are making use of 2 bromine. That is bromine. So that when there is a splitting, one moves along to this, to one comes here, and the halogen is pushed out, which we have to what? This. We are now left with, for example, it can be what? HBr or HCl or HI. So we can have it in this scenario. This is just what? One of the most general equations we can follow in the alpha halogenations of what? Of ketones. So this is the general equation we can have. So we have the one of our common examples we want to use is what? In the alpha halogenations of what? Of ketone. We have acetone here. We are acting with bromine, and in the presence of when we have our base, which is sodium hydroxide. Now, what do we mean by acetone? This is a ketone group, an acetone. An acetone is also known as, if you don't call it acetone, it's also known as what? Propan-2-one. So if you don't know it as acetone, you either call it as what? Propan what? 2-one. So acetone is just the common name for propan what? 2-one. So this is our normal naming. We have carbon 1, 2, and 3, which makes it it has the longest chain, which is the longest chain, and we have ketone attached to the what? To the carbon 2. So now, to generate the first one, when you talk about the alpha halogenation, the first step is to what? Is to locate. Step 1, locate the alpha hydrogen. Locate the alpha hydrogen. So in this scenario, since we have a balanced equation, we can say this can be the alpha hydrogen, or this can be the what? Alpha hydrogen. Since we have it balanced, both left and what? And right, you can successfully or willingly choose one between this and what? And this. So we can start from here, or we start from what? From here. So this is a free will of our what? Of our reaction. So you can see this is a what? Free will of our what? Of our reaction, but we can decide to start from here. So now the next thing is we need to cleave our base. We have Na plus OH what? Minus. So when we cleave our base, we are left with, so this would attack our alpha hydrogen, and we are left with this H3CO CH2 minus. We can see, and this is said to be very active at this moment. You can see it's very active. The next thing is to what? Introduce, since we form our enolate. So the next thing is to what? To introduce our bromine. So we want to introduce our what? Bromine. So we have this bromine attacking this carbon, and we are left with resulting to what? To this. Resulting to what? This. CH2Br. So you can see we successfully alpha halogenate this ketone group. And don't forget, we have one bromine remaining here and the hydrogen that was pushed out at this point, so which result into HBr. So you can see we successfully halogenate our what, our ketones, and we have our what, hydrogen bromide. So that's a successful mechanism using what, acetone. Okay. So now we have this compound, and so we are trying to alpha halogenate this ketone group. So this is an aromatic ketone. So we are trying to what, alpha halogenate. So this is what. So now, what is the name of this compound? Drop it in the comment section. But now, this is, drop the name of the what, of the compound in the what, in the comment section. So we are trying to halogenate this what, particular compound. And don't forget, we are using sodium hydroxide as a base. We can be dilute sodium hydroxide, or can use pure sodium hydroxide. So the first mechanism is, as being stated earlier, that is locate your alpha hydrogen. The first step is to what, locate your what, alpha what, hydrogen, which you can figure it out here. You can figure it out what, here. So this is where we can locate our alpha hydrogen. The next thing, split your base. We have sodium hydroxide, we are left with Na plus and what, OH what, minus. So when this attacks, our alpha carbon, we are left with, so we form our enolate. So an enolate is being what, formed. We have this. So we have this. So we form an active site. So an active site is already being formed. So now the next thing is to bring our what, our halogens. Our halogens. So we bring in our halogens. We have this. So this attacks at this point, which leads to the formation of what, of this. So, and don't forget, we have our bromine, which can also bond with this. So we can have plus NAB what, Br. Can also have this. So now there's a general name for this. We can say it will be alpha haloketones. The name can be derived from alpha haloketone. So that in simple terms, you can say this to be what, from alpha haloketones. So alpha. So what is our halo group? The halo group is the what, bromine, and the alpha halo what, ketones, and the name of the ketone is called what, acetophenone. You can see it, our alpha halo what, alkanes. Why the previous one, the previous example that was used is alpha bromoacetone, is what, alpha brom. So now our next reaction that Carbanions undergo is what we call the nucleophile